Okay. Alright, that should be it. Okay, good. So my mic is working. Alright, good. Now, hello everyone, welcome back to another video. Now, I've done some off-camera work, so I've basically created an instruction set architecture for my custom computer, right? And so I decided to do this before actually making a code writer, a code generator for my custom parser. Here, there you go, for my compiler, right? Programming language compiler, right? Um, yeah, so I basically made a instruction set architecture. Moderation helps everyone feel safe. Okay, let me just okay, whatever. So now that we've done that, I think I want to like so I've already tried to create a custom virtual machine already, but my previous instruction set architecture was really complicated. Not really complicated, but a bit redundant and it's not that good. So instead, I revamped it now, yesterday that is, and so with this revamp, I think I want to like actually create an emulator. Um, so first of all, I've already created a kind of test suite kind of thing for this emulator. So yeah, so we've got the ROM for the CPU, and then you've got the start state, which includes the registers, and the end state, which includes the registers and things like that. Okay. And then also like you can like try to compare the memory of the computer in the test kind of thing um to see if if it did what you wanted it to do. So now what I want to do is to like edit this which is the execute function for my emulator. Actually, before that I wanted to yeah update the do cycle function, which involves getting the next memory unit to find the instruction, right? According to my instruction set architecture. So I think we can like, yeah. So the instruction is, of course, the least significant 32 bits of the instruction unit, which is a 64-bit double. Right. So comment this out, and I'll just comment this out as well. Okay. So now what I want to do is follow the instructions. So the instruction set architecture. So what do we do here? Where is it? So the registers. Here's the instructions. So yeah, so this is the last 32 bits. Right? The not the last. Well, yeah, the least significant 32 bits. So instruction proper. So that means the okay. So that means we can first separate it into instruction proper and internal data. So inst proper luau 2-bit 32. Actually no, we'll do luau 32 extract because I'm planning to make this a luau just a scripting language used by Roblox. So I wanted this to be convertible into luau because I want to incorporate this eventually into some sort of game, Roblox game. I don't know if that'll even happen, but whatever. So yeah, we want to extract a number of bits. So the value we're extracting from is instra, and then so we want the bit position A. So that would be the first. Yeah, that would be the upper 16 bits. So that would be the 16th bit, and then the width would be 16 bits. So it's a short, basically, in POSIX terminology. Okay, and yeah, so that's gonna be that one. That's the instr proper, and then we've got the internal data. So that would be the lower 32 bits, lower 16 bits. So instra, yeah, and then yeah, so the lower, yep, we're starting at bit 0, and we want 16 bits from there. So that's the internal data. And again, we can get the opcode. So opcode is equal to as a number, right? Number. I don't think we need to make this let. I think we'll just set it to const. Luau bit 32 extract. So the opcode is the lower 8 bits of instr proper, of the instruction proper. So instr proper lower 8 bits. And then we also want the what do we want? Okay, that's 8 bits. So here, we want how many mem units? So external argument info. So external args info, I guess. And then, yeah, that's the upper 8 bits. Well, actually, not really. It's just 4 bits. But we'll do 4. We'll do 8 bits, because why not? Opcode, okay, Mr. Proper, okay, that should be good. Now, we want to actually process this. So what we actually want would be, actually not just external arguments info, it's just arg info. Args info, sure. And then now we want to analyze each argument. So, analyze args info to see if we need external arguments or what kinds of arguments there should be like a whatever what kind of arguments they are. So what do we have? Scroll up. Actually, let me like compress some of these functions right here. Yeah, these luau functions. These functions which mimic luau behavior, which I wrote, well, with the help of AI. Some help at least. Just hide these. Okay, so now that we have this, what we need to do is read. Okay, so it says here how many mem units other than instruction does it use, right? So now the CD is argument 1 and A, so bit CD is argument 1 and bits AB is argument 2. So we'll do that. So const AB arg1 info number would be the lower 2 bits of args info. And arg2 info would be the second lower 2 bits. Kind of, I don't know. Yeah, kind of. The 2 bits that's like before the lowest 2 bits. Yeah, whatever. That's gonna be argument 2 info. So this is gonna be AB. So bits AB and bits CD. Actually, no, this is bits CD and this is bits AB. So okay, what do we want? We want to get rid of this. Okay, let me get rid of this. That's the old version. This is instr proper, which is not what we want. Wait, isn't that what we? No, we want it to be from args info. There's a bug right there. Yeah. Good. So what do we want to do? Hmm. Okay. Well, first of all, we want to see, okay, arg1 and arg2. What is argument 1 and what is the value of argument 2? I think I want to pass to the function um to this dot execute. What we're gonna pass here is we're not gonna do this. We're gonna change this to um argument 1 as value and then argument 2 as value, then argument 1. Okay. Set argument 1, set argument 2. Because I want this to be like modular or something. Okay, get argument 1, get argument 2. Well, no, this should be argument 1, argument 2. Because I want this to be like modular, and instead of number, it's going to be a function. How to type a lambda function. How to, not type, how to, typing TypeScript. How to type annotate a lambda function TypeScript. TypeScript lambda function, how to type annotate if the argument of a function is a lambda. Okay, okay, let's just use Stack Overflow. Is a function. Yeah, something like that, yes. This is what I'm literally doing. Yeah, wait. Yeah, something like this. Okay, let's not get copyright infringement with this advert. I think it's a terrible advert. Kind of. Okay, I'm just trying not to copyright infringe, so I got it. Okay, anyway, so you got function. Oh, okay, so you got argument, and then it returns the result. Okay, that should be fine. Okay, so this one, get argument 1 is going to be a function. It should return a number. Yeah, yeah, that works. Okay, good. So, yeah, I'll do this as well. What does it say? What's inster byte? This should be a opcode. Okay, now I think we can like define some of these functions. So get arg1, we'll set that to a lambda function. Yeah, so it will return a number. And okay, so now I guess we could just do the if statements here. So if, for getting argument 1, so if we do arg1 info, if the bottom bit is 1, I don't know. If the bottom bit is 0, um Is something wrong? Oh, whoops. Okay. So if that's the case, then we just do return no argument actually. So we'll just make it return a special value. Let's just say let's say that. And so okay, else if so else that means there is an argument. There is an argument. Actually no. First of all, if argument 1 info is 0v11, so this would be register argument. So that means first of all I'll make variables for int data. So analyze int data, not analyze, split int data into to get specific information on arguments. So we'll just do like const arg1, okay, internal arg1 data is int data. No, we want to get 32b extract instr, so the first 8 bits, the lowest, least significant 8 bits, and then the internal arg2 data, the higher 16 bit, the higher 8 bits, not instra, but this should be int data, sorry. Okay, now if this is 1 0, then this is a register argument. So like I'm just gonna return uh what's this called? What am I gonna return? Well, this dot get register, and the code is gonna be arg1 info. Actually, not arg1. Alright. Okay. Not arg1 info. Wait. Let me just 1 moment. Battery. Okay. Let me just. Okay. Should be fine. Okay. Wait. No. We want to get register, and what's the register code? Well, it's arg1 info. There is a. Yeah. So if this is 1, then there's an external argument. So either it's memory argument or not. So we're first gonna need the byte. Okay, wait. So if I create logic, so read more bytes into memory as necessary given the number of external arguments needed, required. Sorry. So we'll just do like for let I is 0, I is less than arg1 info at 1 plus, okay, we'll just plus arg2 info at 1. That is, we're going to add, this statement is basically saying, hey, is there an external argument that is needed for argument 1, and is there an external argument that is needed for argument 2? And if both are true, then we're going to like get 2 more bytes. If none of them are true, then that's fine. But whatever. So actually, I don't think a for loop would be useful. I'll just do if arg1 info at 1. If this is true, that is the lowest bit is 1. And that means of arg1 info, that means there's is external argument needed, okay, given for arg1. If so, we're gonna say let arg1 external arg1 byte be equal to yeah, I'll do that. Not byte, but mem unit, because each memory unit in my instruction set architecture is 64 bits. Yeah, and that's external arg1, external arg2. Okay, we'll do that. So is external argument given? Okay, if so, we're gonna do x arg1 mem unit is equal to this dot get next unit. We're not gonna else if, because maybe argument 1 is not given, but it could be that both are true, that both arguments do require external arguments. So external argument given for arg2. If so, we're gonna set x to arg2 mem unit to get next mem unit. So now we have that, and then now there's an external argument. We're gonna say, hey, if arg1 info at 1, well, not at 1, at say that this one is equal to, well, it's either 0 or 1, so whatever. Okay, if this bit is set, then that means using external argument, okay, it's a memory reference, so return this dot memory dot get unit, and what is the address? It's going to be external argument 1 mem unit. So okay, now else we're just going to return the actual mem unit. Whoops, as a value. So that should be fine. So let's see if this logic checks out. So get argument 1, what are we going to do? We're going to look at external argument 1 info. So is this bit set? No, if it is exactly equal to this, then that means it's a register argument. If the least significant bit is 0, that means there's no argument. You can return a kind of special value. If there is an external argument, yeah. And yeah, if there is an external argument, that is this is 1, that means if we yeah, so that means if this bit is set, if the second bit, well, it's the first bit if we 0 index, the penultimate least significant bit is set, that means the value, the external argument is a memory reference, so we have to reference memory using the address given. But if it isn't set, then that means it's used as a value. So it's the external argument itself as a value, and it's not to be used as a reference to memory. So now that should be fine. So that's get argument 1. Now we want to do get argument 2, which is basically the same, except we just use get argument 2, right? So we have to change everything. So argument 2 info, this dot get register argument 2 info. Else if argument 2 info, no argument actually, turn that. This would be if argument 2 info, is this one, memory reference, this one, argument 2 at value, argument 2. Good. So now if I do comment this out, Yeah, the error should be an argument 2. Yes. Wait, what is argument 2 info? Yeah, no, there shouldn't be any. That should be fine. And then if we do comment this out, that means this should be, argument 1 should be having errors. And yes. Yes, I like that. I like that. And now we want to do something similar, but it's for setting the arguments. So now it's set arg1. And now we're given a value. And we're returning a void. So if it's a register argument, we're going to do this dot set register argument 1 info to the given value. And if it is no argument, then we're just going to fail silently. Fail silently. Yeah, I was reviewing the code with Chat. I was making ChatGPT review the code like last night, and so ChatGPT recommended saying that this is called failing silently, which yeah, that makes sense. Okay, so there's an external argument. So okay, so if it's a memory reference, then we can do this on memory.set unit. I'm gonna set this to value. The value at this address too. This value or address, I don't know. And so if it is a value, then we're just gonna fail silently. And we're gonna do the same for set arg2. That means we can like change. Oh no, no. That means I can't control. Okay, yeah. Well, that's that. Okay, so argument 2. That argument 2 info. Wait, why is it argument 2 info? It should be argument 2. Oh, it should be. Oh, there it is. There's the bug. Here we have a bug. Get register should be that. And then set register should be that. Internal arg1 data. And then internal arg2 data, it should be here. That should be get register. This is just the information about the data, not the data itself. So yeah, so we move down here to there. arg2 info, arg2 data info. Okay, this should be arg2 info. External argument 2 unit. Argument 2. Okay. So that means if I comment the information on argument 1, yeah, so this should fail. Yeah, this fails. That's good. This one does not fail. This one fails as well, as it should. This one does not fail. So, okay, if I do the same, but it's for argument 2 that I comment out. It's argument 2 that argument 2 data that I comment out. Yep, that fails. This doesn't. This fails. This doesn't fail. Oh, this fails. I like that. I like that. I like that. Good. So now, now that we have these 4 functions, now we can actually get to do what we like to do, which is actually do the opcodes. So first, wait, no, what about the external arm? Oh, wait, no, we already have that here, right here. All right, I like that. So now what we can do is, okay, now we can actually do the switch statement where we can do the opcodes. So opcode, to be sure, that is it insta proper top 16 bits the first? Yes. 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 Insta unit number is equal to this dot get next unit. I'm not sure. Oh yeah, yeah. Yeah, that's good. This is gonna be a halt instruction. So we're just gonna say, hey, we're just gonna halt. But in order to do this, we're just gonna uh this dot set register. Wait, now I need to update the codes, the register codes, because I updated them. So yeah, no. So it's IP, then SP, then RF, RA, RB, RC, and RD. So let me check the. Okay, let me see here. Okay, so it says here, general purpose. So it's it's FS now, not S. No, okay, SP, IP, then SP, then FS. So sorry. Okay, so now IP, then SP, then it's not RF anymore. It's called RS. So this is 0, 1, 2, 3, 4, 5, 6. Yeah, I think that's okay. Port nums, motherboard, keyboard, mouse. What's P store? Permanent storage. Permanent storage. Motherboard, keyboard, mouse. Okay, now, okay, yeah, so this is IPSPRF. No, this would be FS, which means flags with an S at the end, flags. Yep, and then, okay, that's good. And then now ports, yeah, we got 256 ports. I'm gonna initialize ports. This on memory is equal to memory. I could make this a const by using and then just use a lambda function, but um okay, now what do we do? Okay, now what we want to do is let's go back to the halt instruction. So we just do this dot um set register, this dot so what's okay, this no CPU dot register codes. I have a feeling I don't want it to be an enum. Kind of just want it to be a static like thing. Know what I'm saying? Like it should be RC IP RC SP. Eh, whatever. CPU.regcodes.ip, and we're gonna set this to this .get register. CPU.regcodes.ip -1. Make sure that the instruction pointer will always stay at this instruction. This halt instruction. Okay, so the next one we're gonna do is we're gonna do move. And this is simple. So it's just set argument 1 to get argument 1. No. Set argument 1 to get argument 1. There you go. No. It's not doing anything. There you go. Set argument 1 to get argument 2. So the value of argument 2. I'm gonna break this case. Okay. What's the next one? Move. Add sub Maldiv. Oh, Maldives. Wow. Okay, let me put on Notepad the list of instructions. So we got move, add, okay, 0, 1, okay, 0, 0 is halt, 0, 2 is add, 3, I'm kind of lazy. Add sub mo div idiv, which is integer division, left shift, right shift, and or not. Oh, I was gonna add XOR, no? Yeah, I was gonna add XOR, so I'll do that. Not BC, I'll add XOR arg1, arg2. I feel like that should be right here. That should be C, D, E, F, 1, 0, 1, 1, 2, 3, 4, 5, 6. Okay. So and or XOR. I feel like what would be easier. Okay, let me just like copy all of this. Like, let me just copy the comment here. Yeah, so this is definitely not. Okay, we'll just do this. Okay, should be fine. And then now, I'll just remove the additional things unless it's needed. So, yeah. Now we'll just do add. So case hex 02. Yeah, so I'm going to set arg1 to what? Get arg1 plus get arg2. Case hex 03. Okay, set arg1 to one moment. Okay, so now yeah, we're gonna, this is a subtraction, not a multiplication yet. So let's get arg1 minus get arg2. This might be unclear though. Let me go to sub arg1 equal to arg1 minus arg2. Yeah. Now we're gonna do multiplication. Well, this is literally just the same. It's just that different operations. Okay, we'll do comparison later on. Okay, I need to make sure I update the opcodes. So hex 02 add, hex 03 is subtraction, Hex 04 is multiplication, so I just multiply them together. Hex 05 is division, so I need to change this to hex 05. Division 6. Wait, does integer division work? So 1.4. Oh, JavaScript integer division. How do you do that? Did you just truncate it? Is that what you do? Oh, that's literally just it. Math.floor. Okay. Um, Wait, but is that gonna work? So math.floor. Oh no no. Yeah, that's not gonna work. Okay, so that means I'm gonna need to make another luau function. Oh dear. Okay, function luau math floor um b number returns number. So I'm going to do a return math.floor v, but it can also be return something like that. Okay, so now that's math floor. We can also do like integer division. So luau integer division. Is it the same? If I do like print math.floor 1.4 divide 1 and print math dot, okay. If I do this, unexpected symbol. Oh wait, no, you need that. Oh, is it this one? Huh. Luau is integer division symbol is math.floor I, okay, a b equivalent to a. For numbers, a is equivalent to math.floor idiv meta method. Oh, cool. This is luau right here. Okay, so we can literally just do that. Okay, good, good. So, yeah, lure. Well, we'll just do idiv. A1 number, B1. No, we'll just AB. A number, B number. Results in a number. We're gonna do return. Luau math floor. A divided B. Okay, this is the old version. Um, div. Okay, there you go. That's division, and then idiv hex 6. I'll just do this, and then oh no 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 no. Isn't that comma? Isn't that the comma operator? Okay, and then idiv which is weird because it's JavaScript. I don't expect it to behave like that, but whatever. Luau idiv. So LSHF. That's hex 7. Set arg1. I think I should like get rid of these first so that I can like so that I make sure to like update them. Okay. Hex 07. It says left shift. So we're gonna set argument 1 to get argument 1 left shift. No. We should use the I should use the function that's what I use. So be left shift. Let's do this. And then do the right shift as well. So that's hex. The opcode is hex 08. Set argument 1 to right shift. So that means luau bit 32 R shift. And I'll get rid of this comment right here. I wonder, so if I do 1 over 0 infinity. Oh, okay, so that's what. Okay, good. Whatever, I'm getting distracted. So that's division. Okay, multiplication, division, integer division, left shift, right shift. Okay. R shift. Okay, now we want to do AND. So 9, I do luau bit 32 band. Hex OA. Or, so luau bit 32 bore. XOR hex OB. So hex OC. Luau bit 32 not be not. Now we're just gonna compare. So hex, okay, OD. Okay, so const comparison. We're gonna do so the compare results will be start at 0. So we're gonna test. Okay, if arg1 if get arg1 is less than get arg2, that comp to 2, else if get arg1 is greater than get arg2, we'll return 1. Oh, not return, we'll set comp to 1. And if it's neither, that is, if it's equal, then comp is 0. So, but I already set it to 0, so it's fine. And then now, I just need to set the flags fs. So, okay. So this dot, I think, set flag, let's say. And flag 0 would be, okay. No, add 0. Okay, so that's going to be this dot, not this, CPU dot flag position dot CMP, I think. Compare, comp. And then the value, not vol, there's val. I guess you can read it as well. Anyways, not VOL, okay, because I misread it kind of as VOL, as in like volume or something. But anyways, it's value. It's going to be value of compare, of comp. And then the width is going to be 2 bits. And then now, we're gonna do hex OE. So we want OE. Okay, let's not get distracted by the instruction at the top. So if this dot get flag, get flag, okay, okay, this dot, oh yeah, I should probably update the get flag function, method that is, to get its width. So width is number 1. Pause, and then width. So if this dot get flag at CPU, whoops, CPU, nope, CPU dot flag position dot comp, the width is 2 bits. If this one is equal to 0, then it would jump. So we'll do this dot move, no, yeah, this dot get, no, this dot, no, not this dot, set arg1, there you go. No, not set arg1, we just want to set it. Okay, yeah, we want to set the register, this, no, not this dot, CPU dot regcodes dot IP, and we're gonna set the value is gonna be, get arg1. Okay, so then if it's less, we're gonna jump if this one is equal to 1, 0. So that's 2. That means A is less than B. Is that right? Whatever. Okay. JL. Okay. Yeah, we're just cutting that. Okay. And then we're gonna take this and we're gonna copy this to JG, which is jump if it's greater. That is if the flag result is this one. So now, we do, okay, this dot set register. Yeah, we'll do that. Okay. Then now we can do push. And what push does is that, okay, well, case hex11, so the output is hex11, hex11 that is. So we'll do this dot set, no, this dot memory dot set unit address is gonna be this dot it's sp minus minus. So okay, so get register this CPU dot regcodes dot sp. So where the stack pointer is, we're gonna set that the address that it points to is we're gonna set that to argument 1. So get argument 1, not the semicolon, and then we do this dot set register cp dot reg codes dot sp2 this dot get register cp.regcodes sp, and then we minus that by 1 because we want to decrement it. And now we want to do the same for pop, but now we want to increment it. That is, we want the stack pointer to go up to higher values of the memory because the stack starts at the top of memory. But first of all, what we're going to do is we're going to do the increment first, and then we do the get unit. So this dot set register, not set register. We'll do set arg. Set arg1 to this dot memory dot get unit. I'm gonna set it to this. Just add semicolons there. We're gonna set argument 1 to the memory unit at sp once it has already been incremented. SP stack pointer once it has already been incremented. Did I say decremented? Should be incremented. And now we'll continue with scall. And what that does is oh, that is something I need to implement later on. Okay. Well, in order to do that, I will need to first create a kind of regular calls thing. So regular calls. Sorry. Okay. So regular calls. Guess we'll do S calls. Because S stands for like seconds. No. S stands for set. Because it used to be like S int means set, which means set interrupt or set regular interrupts in my previous iteration of my custom instruction set architecture. But like here's the thing, right? They're not really interrupts. Like in the proper full-on sense of a real computer where, you know, the state of the CPU is like saved or something. Like no, it's not gonna work like that. So that's why it's just call instead of int. But whatever, let's just not get distracted. So we'll do s calls. So s calls, and it's gonna be an array. An array of what? I like this. What should it be an array of? No. It should just be an array um of a pair. TypeScript type for pair of data. Mm, export type. Okay. TypeScript pair type. Not helpful, but I guess we'll just do an array. No, we'll do an object where the first what it's going to contain is going to be the address. So that's going to be a number. And also the delta, which is not a function, but it's also going to be a number. And it'll be an any length array. So yeah. Do you need to set it? Oh no, because it should be an array. There you go. Oh, so oh, I thought you're not supposed to use semicolons. Okay, never mind. I guess you are. Oh, and these member definitions, member declarations, I guess. Okay, address. Okay, so now I'm gonna put in my to-do make scalls work. Actually do something. Okay, so now what we're gonna do now we're just gonna do like okay, now we're just gonna add the data. So this is instruction 13. opcode hex 13. So now scall. Okay, so now we do scalls. No, this dot scalls dot push. So the address is gonna be regularly called. Okay, so that means that we get argument 1, and then the delta is gonna be get argument 2. Something like that. Okay, and then now we just do decall, so case hex 14 break. So we're gonna do every. Actually, no, this is gonna like push. Should it be like only one regular calling? Because like I don't know if that's needed. Is that really what we want? I don't know if we really want that. 'Cause that's just too much work. I'm gonna get rid of this because this does not seem. Let's call. Okay, S call. Okay, also, okay. Also, a function can have multiple S calls such that yeah, multiple S calls such that uh this instruction these instructions S call let's do that 0 okay 1 okay would cause the function at memory address hex 4920 to be called regularly every 1.0 seconds as well as every 0.5 seconds. Should I just write it in full or something because it's not scientific. It's not SI units really. Well, because we're not doing significant figures here. Okay, seems like no one wrote in the chat, so that means like no one's watching, right? Or maybe someone is. Should they add timestamps? Why not? Okay, so now we have that. Okay, wait, not yet. I just updated the comment here. So, not seconds, but let's call here. Yeah. So we do that, and then for now, decalls. So we're just gonna do a decall. We're gonna do so all instances of all S calls to this function is gonna be off. Not off, yeah, it's gonna be gone. So for let I is 0, I is less than. Is there like an efficient way of like removing something? Okay, I is less than this dot. Okay, no. Luau array length. This dot s calls plus I. So if this dot s calls I dot adder is what is equal to get arg1 we're gonna minus I because okay, and then we're gonna do This dot s calls. Wait, what do I do? Dot s calls. Do I just set it to undefined? What do I even do? Do I need to create a new function that removes throughout array slice? Yeah, well, there's a slice function. So we'll just do this dot s calls is equal to throughout array slice. This dot s calls from where? What's the start? The start is gonna be 0 and the end is gonna be I. Because it's not gonna include I. Yeah. And then we're gonna append throughout array slice array concat. Okay, so we're gonna do throughout array concat. We're gonna concatenate this with throughout array slice. Yeah, this dot s calls what I plus 1 till the length, which will not set. Yeah, so I have that. So wait, so let's see. If let's say I have like uh let's say I have an array that has this is the string hello. Okay. Let array be equal to unexpected token. How is that unexpected? What? Um okay, okay, let array, let's just set it to like A, B, C. What? Unexpected token dot. What is it trying to evaluate? Or whatever. I'm gonna copy this code here. I'm gonna paste it in here. Oh, this is not TypeScript. Oh, you don't even do that? Oh, okay. Well, okay, now I understand why people want TypeScript more than JavaScript. Oh dear. Yeah. You do get used to these type annotations, don't you? Okay. So now let's say we have an array that has one. Okay, okay, this should work. All right, now we have this array. Now we do Lua array s slice js. We'll do concat. We'll just do array.concat because like let's do okay. What do we do? So now we have this. What do we do? So a But we want to remove I is, let's say I is 1, which means we want to remove this middle bit right here, this middle. Elements 0, 1, and then what we do is we do luau array slice jf. A is what, 0? No, from 1 plus 2 would be 2. 2, the length of the array, which is 3. A is not defined. Oh, it's R. The way array length is not defined. Oh. Const luau array length is equal to v. Okay, A is array. No, we're not typing that. We don't need to type, as in like to add a type. Okay, to that thing. So a dot length. There you go. A and C. Yep, that seemed to be what we want. Yep, that's what we want. Okay, good, good. Let's close this up. I plus 1, and the default is just the length. So and then we'll make sure to just say that this is as adder is number and delta is number array as an array of that. And we just do that. So that's how we get rid of each entry that has the address of the argument that is given. Okay. So s calls plus I. On cat. Okay, good, good. So now we just want to set p. So case hex 15. We want to set p. That is setting the port. So we'll do this dot set port. What? This dot ports, I guess. This dot ports. There should be like a function. Set port. So set port code port. Number. If 0 is less than or equal to num and num is less than or equal to less than, there's going to be 256 ports though. Well, actually, we'll just do like n ports. Static n ports. Number 256. And so CPU.n ports. Right, and we'll do, okay, so we'll do this dot ports. Number is equal to, what are we gonna set the, no, yeah, number. What are we gonna set the port to? Is it port number or port code? Port nums, okay. That's, okay. We're gonna set this to a value. So value is number. Else, we're just gonna fail silently. Get port, now we wanna get port value. So we'll just do number. We do return this one, and then else we're gonna return. What should we return? What Easter egg should we do? Hex dead beef. We already have dead beef, and that's when you address an invalid memory. So maybe we can do something else. Let's see. Um, what's the birth date of Canada? Well, when was the Dominion of Canada? Birth date of Canada. July 1, 1867. Okay. So that's hex 1867, July, which is '07, when. Okay. So now, not garbage, I'm sorry. Okay, return a value. Um, I feel like a real port would like have static, would have a different value. Actually, I don't know. Like a real port. Okay, let's see if that's good enough. Okay, so all right, get port, set port. Um, sure, I did. Oh, set p. Okay, so we're gonna do this dot set port. Um, let's set this to a number. So arg1. So get arg1, and then volume is gonna be arg. The value. The value is get arg2, and we're gonna get port. So we're gonna do get port arg1 arg2. So we're gonna do, yeah, this is an exception to the arg2 goes into arg1 rule. So we're gonna do this dot. Okay, I'm gonna do set arg2 to this dot get port get arg1, and that's literally our instruction set. That's literally it. All we need to do now is to like create a kind of user input validation, right? Not input. Not sorry. I need to create a test suite. Um. So I might as well, you know. Okay, now let me just like copy this. Copy these instructions. What's hex 16? That's 16 plus 6, that's 22. Um, uh, okay, we're just gonna like, okay. Now, so I want to like, test this. So first of all, does this even compile? Does this even like a valid code? What is this? Math software, this should be. Okay, good. There's no like errors here. Okay, good. That's all translatable. Okay, good. To luau. Okay, good. Now what do we want to do? So we want to do this. So let me like get rid of this. Okay, let me copy this. What? Oh, that's the custom virtual machine. Sorry. Whoops. Whoopsie daisies. Yeah. We want to do this. There you go. So now we want to do memory address. Oh, wait, never mind. Okay, that's just the assembler. So what do we want to do? First of all, we want halt. That would be hex 000. So 4, 1, 2, 3, 4. So now we're gonna test this out. There should be one cycle. Well, let's do 50 cycles. Why not? Well, the start state, which should be 0. So these are the registers. The end state, IP should be 1. That is the instruction pointer. Let me like IP SP FS RA. What's RB RC RD. Um something like that. Okay, good. So now what do we do? IP, SP, FS, RA, RB, IC, RD. Okay. Now, what we want to do is, yeah, just see what happens. So what do we want to do? Memory chunk. Okay, this isn't important. I'll just like comment this out. Okay. Okay, one moment. Okay. So what do I do? Let's see. Do I just want to test this out now? Yeah, might as well run it. Okay, it's failed. Um, and the failure is that, CPU 0 is equal to 0. So that means IP did not run? It did not. Oh, so it didn't update IP. Oh, wait, no. It should stay at 0 because it's the halt instruction. Okay. Yeah, so this should work. Okay. So we've done that. So it passes. Okay, good. So we did that. Now we do move. Now we can do all kinds of move instructions now. Um, let's halt. I'm gonna do move RA. Oh, we'll do move RA. Let's just get 1672. And then move RB 1.5, 1.6, let's just say. We're using decimals now. And now let's see. So okay. How do we encode this? That's a good question. So, um yeah, this might be a pain. Okay, is this possible? Please. Yes, that's possible. So we want to move to RA. So first of all, what is our argument 1? Well, it's a register, so it should be this. And this one is a value, so it should be like that. So this is be 0, 1. The argument 1 is 1, 0, and argument 1 info is 1, 0. Argument 2 info is 0, 1. Alright. And then, so, okay, argument 1. We want to set, okay, first of all, okay, the opcode should be 1, right? Argument 0, no, argument 1 is RA, and RA has a code of 0, 1, 2, 3, so 3. So this should be a 3 at the end. Well, not a 3. 1, 1. Okay. And then now we do 1672. And the same goes for move RB, but now we're doing B, which is register 4, I guess. We're register with code 4, and we'll set it to 1.6. Okay, let's see. Okay, so now what? We need to update num cycles. Well, that's fine. Registers. Okay, the end state. What should end state be? Now IP should be 1, 2, 3, 4. 5. I'm not gonna count that halt instruction because it's gonna stay there. So 4. Stack pointer not affected. Flag is not affected. RA should be 1672, and then RB should be 1.6. I mean, well, okay. Okay, if we do like 1, is 1 equal to 1.0? I mean, okay, is 1 equal to like, okay, if we do this, so 1. False. Oh, whatever. Probably fine. Let's see if this is this assignment. Okay, passed. Good, good, good. Thanks be to God. Now, let's do some memory addressing. So, what we want to do, okay, how about we make this hexadecimal? Okay, so now what we want is we want to do some memory addressing. Say move to place the place at RA. Oh, look now. What if we want to like reference the value at RA as a memory address? Because we got all of this as bytes, as a byte, I don't know if we need to like compress it to just 4 bytes. Okay, I will need to update the instruction set architecture just a little bit. Okay, that means we need 2 more bits. B, C, D, E, F. Hmm. Just use it as a value, as a mem address. Okay. External is used as a value, mem address. And argument 1 comes from register, from internal register. Either internal as register code or external as next mem unit. That's gonna be that's D. But we're gonna set what do I do? EF? Okay, EF. If EF is equal to like, why is it not aligned? I'm sorry, what? This thing is not fixed with? What? This font is not fixed with. No way. What? That's actually like... editor settings. No way. Okay, much better. Internal as register code. Next mem unit, yeah. 0 or not used at all. So that's EF. There you go. And then we'll do the same for argument for ABC, which is for argument 2. Argument 2, external is used as a value or as a mem address. Okay, wait, let me like edit this so that it aligns. Okay, so this would be bit A, and this is a bit BC. Should be good. And now let's edit the code which, gosh dang it. Okay, that's fine, whatever. So now what we want is okay. Internal one arg data. Arg's info. Here. Arg1 info should be 3 bits. Bits DEF, and this is bits ABC. Okay. Now, okay, if arg info 1, so it's external argument. There you go. That's bit B. No, bit E. Yeah, that's kind of cheap. Not cheap, that's kind of, whatever. Wait, but, yeah, okay. External argument 1 mem unit. Mem unit, internal is. Oh, wait, no. Oh, no, next mem unit. Yeah. That's 0. Okay. I guess we could do this. No, and, hex 2, hex 11. Is external argument used for argument? Yes. Or, I don't know. Oh, no, it should be 1, 1, isn't it? 1, 0. Bit, E. Is it a register code or next unit? Internal or external? Yep, so this is what. Here, so this is gonna be bit C, bit B, something like this. Okay, so now, if we head on over to do cycle, yeah, um, uh, Okay. So now what do we do? Register argument. So if it's a register argument, that means that this is equal to 0. Because it's 1 if it's a memory argument. If it's an external argument. Yeah, so if there's no argument, that is just the last bit is 0. But it should be like 0. Be 3 digits. Because a rule has 3 digits. Okay. Is external argument given for this? Okay. Else if arg1 info and 0b001 is equal to 0. Wait, okay, is this correct? Yeah, so if this is 0, okay, yeah. So if there's not actually an argument, I feel like it should be like this. You should do this first. Else if register argument, we just get register, right? If there's an external argument, okay, that means there's an external argument, right? Whether it's a memory reference or not, it's going to be the least significant of the 3 bits here. So we're going to do this one. So if this is the case, then it's a memory reference. If not, then we just do that. It's either external argument 1 mem unit. So let data, let's just set it to let's set it to number. And let's set data to this. Else let's set data to that. It's gonna be sorry. So if there is an external argument, so if no, this is already else if we know if there's an external argument if not this one, right? It's but this bit right here is equal to 1. No, if let me put that into 1. Right? Equal to 0 b 100. Okay, something, okay, should I just do this? Should I, okay, how do I, like, oh, whoops, that's not what I wanted to do. Okay, so I want to do this, this is going to be a memory, okay, external argument. So it's going to be, okay, this dot data. So data is equal to external argument 1 mem unit. Oh, yeah, that's true. So now we're going to ask, hey, is this a memory reference? So if argument 1 info and so if this bit is set, that's the least significant the most significant of these 3 bits. The least significant, no, the most significant of the first 3 bits. we're just gonna set, okay, memory reference. So value used as memory reference. Memory reference. So what do we want to do here? We want to set data to this dot memory dot get unit data. And then now we just do return data. Okay. Something like this. Okay, let's see if this actually makes sense. Let's go back to the start. We have the instrument unit, not instrument, instruction unit. We got the instruction. Yes. Instruction proper is the upper 16 bits. Instruction data is, no, the internal data is the lower 16 bits. Argument info. Arguments info is the upper 8 bits of instrument proper, not instrument, instruction proper. And the opcode is the lower 8 bits of instruction proper. Now I have integer arg1 data, which is the lower half of internal data. Integer, I mean internal. And internal arg2 data is the upper half of internal argument data, which is supposed to be just 16 bits. Well, actually, it's just it's 64 bits, but you know, we're treating it as 16 bits here because that's what we have here. All right, there. Anyways, so argument one info. So you extract the lower 3 bits of args info. And then argument 2 info, you extract the upper three bits of not upper 3 bits, the, how to describe it, of bits 0, 1, 2, 3, 4, and 5. Yeah, or a C, B, and A, that is. The external argument 1. Read more bytes, mem units from memory as necessary given the number of external arguments required. So if an external argument is given, according to arg1 info, then we do external argument 1 mem unit is equal to get next mem unit. Okay. If argument 2 info says that we do have an external argument for argument 2, then we're gonna also read that external mem. We're gonna read that mem unit as well, and we're gonna increment IP, which is what get next unit does. I'm gonna extract it. So now we have get arg1, returns a number. We have the data, and we're gonna ask, hey, first is this byte, which represents whether there's an argument anyway, right? Is it 0? I feel like I should like do not. I think that would. Is it 0? And if so, okay. No argument actually. There's no argument, so we're just gonna set it to some default value. Or default, I guess. Not really error, but like whatever. Argument 1 info. So kind of like it's valid, but like not the right value. Okay. Now we're gonna ask. Okay, so this is false. That is, if there is an argument for argument 1, we're gonna ask, hey, is it internal or is it external? So we're gonna see the second byte, right? That's the second least significant byte, the penultimate least significant byte, that is. Say, hey, is it 0? Right? Is it not? Is it set to 0? And if it's set to 0, that means it's a register argument, an internal argument. So now we're going to set data to the register, whose code we know is the internal argument 1 data. And else, okay, if argument 1 info, if this bit is indeed set right here, that means it's an external argument, an external mem unit, right? We need to use the next mem unit, which is provided here, so we don't call this twice when get, no matter how many times get arg1 is called, it's not gonna read more bytes to, it's not gonna read more mem units to from memory, so that's fine. However, now we want to get the memory reference. Okay. Now this thing checks, hey, if this bit is set, right, we're gonna treat the data as as a memory address that we need to like locate. So now we're gonna do data is equal to this.memory dot get unit data. And then now once we have data, we're gonna return it. Okay, let me edit get unit so that it's we're gonna need to make sure that it's an integer. Let's see if this Roblox TypeScript support number dot is finite. Is it math dot is finite? How to know if number is finite, Lua. Oh, it's implemented. Oh, this is Luau. Okay, whatever. Okay, whatever. I'll just say that I found a bug. Um, the places where the code checks whether a given number is within a range does not consider the fact that it could be a decimal, a floating, a decimal. Right? No, a real number. There you go. There you go. But that's whatever. I'm gonna go do a cycle. Okay, so let's say we have this. And let's see if we got it correct. If I got it correct. Here, EF, okay, and then D. Let's say, okay, it's used as a value if it's 0, use memory address if it's 1. Okay, it should be fine. Now, what I can do is I can now just copy and paste this for each of the arguments. So, because I don't want to, like, change it, like, no. I don't want to, like, just try to augment it. I'd like to just do this from scratch again. Not scratch, but, like, freshly here. So get argument 2. We're going to change argument 1 info, argument 2 info, argument 1 info to argument 2, int argument 1 data. Else if argument 2 info, data is equal to external argument 2 mem unit. If argument 2 info is this one, data is equal to memory.get unit data. Okay. That's that. And then we're going to do set and then, yeah. Okay, let's set. Wait, why is it? Oh. Now we're going to do set argument 1. So now what we want to do is, well, okay, that's a value. Now what do we want to do? If there's no argument, we're gonna do fail. We're gonna fail silently. Internal register argument. Okay, this dot set register. Internal argument 1 data. Value. It's an external argument. Well, we're not gonna do that. Oh, wait. It's a memory reference. Okay. So you shouldn't actually set that yet. You might want to do this twice. So if argument 1 info and this would be something like move RA. So what we want is this memory dot set unit. Address is going to be this dot get register. Internal argument 1 data. And we're going to set the code. No, wait, just do that. And then we set that to the value that's given. You know, if it is a, okay, but if it isn't memory memory reference, then we're just going to do this dot set register internal argument 1 data with value. External argument. Okay. So that means we're going to do this. We're going to set, instead of this one though, we're not doing that. Oh, we're supposed to use X argument 1 mem unit. Let's see if this code even makes any sense. So let's say we're asked to set an argument, right? Well, yeah. We have a given value, right? We're supposed to set something. This is supposed to return void. Okay, so now, okay. So first of all, is there an argument? And if not, we're gonna fail silently. Else, if there's an internal register argument, that is, if this bit is not set, we're gonna, okay, that means we want to set something. So it's either move RA or move RA. It's either one of these two. So it's either one of these two pieces of code, right? But the thing that discriminates between these two is whether this bit is set, right? And if it is set, then that means it's a memory reference. It's this one. I'm gonna set unit. We're gonna get register value of RA, say RA, and then we're gonna say, hey, yeah. So we're gonna get that, and we're gonna set it to this value, the value that is given. But if it isn't, then that means it's this one. We're just gonna move it to the register. We're gonna set register or copy the value to the register. So we're gonna set register to that value. Yeah. So else, if it's an external argument, that is this one is set right here. This bit is set, and remember this bit should be 1 because of this statement right here. This if else. But since this is if yeah. Since this is a 0b 0 1 0 yeah. Wait, what? Okay. Anyway, so if this bit is set, that means it's an external argument. So now we do hey. Hey. Yeah. So we're gonna check, is it a memory reference? And if it is, we just set the memory at external argument mem1 argument 1 mem unit, so the byte after, to the value. Else we're just gonna fail silently. Okay, but okay. Let's say this is false. This is true. This is either true, either false. Yeah, I think this is redundant. Is this be true? Or it could be false? I don't know, is it, yeah, this would be 0. This code would run. If else, it would run this bit of code. And then if this is 0, it'll run this bit of code. If this is 1, then it'll run this bit of code. So I think it's fine. I think this is what's it called? I think not needed. Wait, it's called what's it called? Redundant. Okay. So now we can now set argument 2 finally. Just need to change the names. So set argument 2 to value. So now we do argument 2 info. Argument 2 info. Argument 2 info. I'm gonna remove that because that's not really the case. Because we're not really gonna set argument 2 directly, at least. Like that port instruction get p. Yeah, that's not setting argument 2. That's gonna set the port at. Oh no, it is setting argument 2. Okay, whatever. But yeah, it's not gonna distract you here. So yeah, memory reference. And I think it makes sense to separate those get and set ports from the normal, move instructions. Okay, I'm getting distracted. So now what do we do? Memory reference, we do this. Okay. Now what do we do? What am I thinking? Okay. This should be argument 2 info. Should be into argument 1 data. Should be into argument 1 data. And this should be argument 2 info, just in case I uncomment this code. Argument 2 info. Argument 2. Okay. Get arg1, get arg2, set arg1, set arg2. So do I just want to wing it now? Or do I want to, yeah, I want to run it, see if it works. Yeah, I'm a bit impatient, but let's see if this works. Wait, no, I need to redo this bit of code right here. The this is called the argument info byte. Well, I guess byte, yeah. Portion, yeah, 8 bits of this memory unit. Well, really, it's 6 bits. It's these 3. I'm getting distracted. So now, what do we do? Okay, so for argument 1, this one, yeah, we do have it. We do use that. So what type is it? Is it a register or is it an external? Is it an internal or external argument? Well, it's an internal argument because it's RA. Okay, and it's encoded here. No, that's not encoded there. That's not right. It should be encoded here. Oh no, that's the instruction. Okay, it's encoded here. And RA is okay, 0, 1, 2, 3. Yeah. Register with code 3. And it's 1, 1. Oh wait, no, I already have it here. Oh yeah. This is for argument. Yeah, okay, let me repeat. This is for argument 1. This is for argument 2. This is for the opcode, and this is for the how many arguments, like, yeah, it's argument info. Yeah. Well, really, technically, it's these 6 bits, but I already said that. Okay, yeah. So yeah, we're using argument 1. We have argument 1, that's RA. It's an internal argument, and yep. And then is it a memory reference? No. Okay, for argument 2, do we use it? Is there an argument 2? Yes. Is it internal or external? It's external. External. So, wait, no, if it's internal, then it should be 0. If it's external, it should be 1. And then if it's external, internal, wait, what else? Okay, is it a memory address? Is it used as a memory address? The answer is no. So, yeah, we'll do 0. And, yeah, I think that should be the same for this. So that register B, yeah, it should be at 1 after this. So that's good. I think that's it. I think we can run this. Oh, it fails. Okay, this should be... Okay, passes. Good. God be praised. So now, we're going to halt. Okay, now we want to say, hey, we want to move to RC, the value at RA. No, we'll first set the value. So RA, we'll set that to RB. So let's see, how do we encode that? Well, let's do move opcode. Okay. Alright. So let's look at the arguments. Argument 1 is used, yes. Is it register? Yes. Is it used as a memory address? Yes. Okay. Is it argument 2, is it used? Yes. Is it register, or is it internal or external? It's internal. So 0. And then if it's okay, and is it used as a memory address, or is it used as a value? It's used as a value, so that's going to be 0. And then now, let's look at the actual arguments to put. So RA is 3, so we'll do this one. RB is the second argument is 4, register with code 4, that is. Yeah, with register 0 being IP. And then, okay, now let's update num cycles, that's fine. This is how many instructions? 1, 2, 3, 4, 5. So we're going to update IP to 5, the expected value of IP to 5. But now, what does this mean? What does this have to do? Okay, so that means the memory value at RA, which is hex 1672. So we're gonna have a memory chunk here. So start address is gonna be 1672, ending is 1673, and it should have a value of what RB is, which is 1.6. Right, let's see. Okay, it seems to pass. Okay, good, good, good. Okay, good. Let's continue. All right. What are other things? I think we'll do move. Okay, we're gonna move. Cause okay, we have direct values here. Indirect, yeah, memory addressing. So what if we just move on and let's do add RA to RA. We're gonna add whatever is in RA. Yeah, and that's okay. The add instruction has an opcode of 2. Okay, assembly is hard. Assembling is hard. Like manual assembling. Okay, so the first argument is, yeah, that's the first argument. Is it a register? Yes. Is it used as a memory address? No. The second argument, is it used? Yes. Is it a register? Is it internal or external? It's internal, so it's 0. Is it used as a memory address? The answer is yes. Now we just do okay. Now what are the arguments? RA is 3, which is 1, 1, and then also the second argument is 1, 1 as well. So now this is gonna be IP is gonna be 6. What is this? Okay. So now what is RA? What is RA gonna be? Well, we're just gonna add 1.6 here. That should be its value. Let's run it. Okay, it passes. Good, 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 good. Yeah, so now we can basically test the various like memory things. So I'm assuming add, subtract, multiply, divide are all gonna work the same because I basically just copy and pasted them. Our add, subtract, multiply, divide. What's the emulator for? Oh, hello. That's a good question. Oh yeah, so I have a custom instruction set architecture. So it's basically a computer that I made up. Yeah, and so the emulator is supposed to do that. It's because I have I guess a compiler for like a custom programming language, and before making a code generator for that, I was thinking, hey, I need to make an instruction set first, so I know what code it should generate. But yeah, and so this this custom like computer architecture thing, in the future I plan to like integrate it into like a video game or something. Um, so yeah, that's basically what the emulator is for. Right now, I'm basically just verifying whether my emulator is working correctly, whether it's interpreting the instructions correctly. Um, but yeah. Okay, so I think the arithmetic instructions should be fine. I think that's, yeah, it should be fine. Arithmetic, it should be fine. Oh yeah, and the game is, the future game is gonna be on Roblox. So as I write this TypeScript, I keep in mind that I have to convert it to Lua, um, using this web page conveniently. Okay, but yeah, okay. Um, but I think, so this, all this arithmetic should be fine, I think. Or XOR argument one, okay. Yeah, so there's gonna be compare, comparison, jump if equal. Okay, I think I want to test these comparison and jump if equal instructions. Okay, comparison and jump if equal. Okay. Uh, well, okay, whatever. Okay, so if I compare, okay, it should be, yeah, compare. If I check my code, okay, arg1 is, okay, that should be fine. Yeah, so I'll just compare, let's say, 2 and 1, 1 and 2, 1 and 1, and then I'll compile it. Okay, jump if equal to, say, 200, jump if equal, uh, I'll just set IP to undefined because I don't want to. Yeah, so right now I'm basically testing it out to see if it's doing what it's supposed to do with whatever instructions. Okay, whatever. So now, jump if equal, jump if less, jump if less, jump if greater. Is it like an interpreter? Yeah, well, yeah. It basically does interpret the instructions. So yeah, it is basically an interpreter of bytecode. I guess you can, yeah, you can consider these long string of numbers as bytecodes, like Python. Yeah. Okay, so we want to compare. Oh gosh. Manual assembly is so hard. Like, what the heck? Okay, so we want to compare. So what is the opcode for compare? Hex D? What is that in binary? Hex D in binary. 1101. Okay, good. Good to know. 1101. We have two arguments. So yes, we have an argument. Argument one is used. It's an external argument, and it's gonna be a value. Okay, and the same for the second argument. So the first argument is 2, 1. Okay, good. Jump if equal. Okay, how do we even do that? Okay. What is the opcode for jump if equal? Hex E, and okay, so that's okay. Oh my gosh, manual assembly is so hard. Like, imagine, like, back in the days, like, I don't know, in the 60s or the 50s or whatever, like in universities, people would be manually assembling their code into like punch card or something. Okay. Okay. Um, okay, what's the opcode? It's the one after compare, so we'll just add 1. Okay. So it only has one argument. So it's used as a value. Hex 200 JL, that'd be this one. Should be 300. So this code should jump to the memory address at 300 if this comparison is actually never mind. No. 2 is greater than 1, so it should jump to the memory address at 400. That's what it should do. 1, 2, 3, 4. Okay, now I can now compare at the end state. IP should be at, by the end of this, at hex 400. Hex 400. So that should be, please work. Yes, it works. Good. Does what it's supposed to do. And so if I change it to like 1, if it's equal, that this should be jump if equal. This should be 200. Okay, it works. And then if it's less, so 0, right, so 0 is obviously less than 1. This should jump to 300. So its ending instruction pointer should be hex 300, sorry. Are you working? Yes, it works. Okay, so that means the conditional jump instructions are definitely working. We are not gonna do this though, because we don't want to do that. Yeah, we want to do other tests. Is that okay? So now let's see if we can test other instructions before I go. We could do push and pop. So maybe we could test out functions. But like, okay, at this point, maybe I should just literally just make an assembler. Yeah, I think, yeah, at this point, I should make an assembler. And then, once I make an assembler, I can make the actual code generator for my compiler, which would actually turn the abstract syntax tree, the parse tree of the code into bytecode, or the instructions for this like virtual machine architecture. Which should be exciting. Okay, that's good. Oh yeah, so we want to test out, what the heck do we want to test out? I don't know, man. Like, man, we come from poverty and we ain't out a thing. Okay. Push and pop. So we're gonna push, let's say IP, and we're gonna like do some sort of calling, like, ROM. No, I don't want to call, whatever. We're just gonna push like some numbers. Let's say we just push IP. Let's just push IP. Why not? We're gonna push that instruction. Okay. Oh dear, oh dear, oh dear. 1, 2, 3. Okay, good. So now we're gonna push, and what is the opcode for pushing? To the stack. Hex 11. So that's like 16 plus 1. Okay, good. Good to know. So it's 16 plus 1. There you go. And then it has one argument, and it has one argument, yes. So argument 1 is used. It's a register, yeah. It's an internal argument. It's included within the instruction byte, not byte. 64-bit like memory in it, I guess. And it's not used as an address. It's just used as a value. So now what do we want? So for argument 1, we want the instruction pointer register, which has register, which no, whose code is 0. There you go. So yeah, now at this point, we know we need to first set stack. Okay, we need to first set up the stack. So we're gonna do like uh, move sp. We're gonna set it to like 7ffff. That should be where the stack is. So oh my gosh, this is like torture. Okay, yeah, time to like manually assemble again. Okay, move. Yeah, just the move opcode, which is 1. The first argument is, yeah, there's an argument. Yeah. The second, no. And the argument is a internal argument is a register code, and it's used as a value, not as a memory address. And then we'll do, and then there's another argument. It's an external argument, meaning it's like outside of the actual instruction 64-bit unit. And then, well, this is 32 bits, but yeah, because JavaScript stores numbers as 64-bit doubles, it's 64 bits. Anyways, and it's used as a value. It's not used as a memory address, so that's fine. Yeah, so this should set stack pointer to. Okay, first of all, let's test if this code even does what I want it to do. So stack pointer is here, and we expect it. That's the start state. Stack pointer is here. We're gonna expect stack pointer to be at hex 7ffff. Fail. What happened? CPU 1 is at 0 instead of that one. Oh, did I do something wrong? Okay, so it's fail, and it's how's it 0 when? Oh no! Here we expect it to be this one, but then it's not. Oh, then what then is? Oh, we set this to the instruction pointer. We don't, oh my gosh. Oh, see, okay, yeah. This is why assembly is so like, yeah, we need to. Oh dear. Yeah, so we want this to be a register code 1 because SP has a register code of 1. Okay. There you go. It passes. Good. So that's what we want. And then now we can push instruction pointer to the stack. The value of instruction pointer anyway. And so now we go to the memory chunk and we're gonna check. Hey. Is the byte at 7 hex 7 ffff at 1? Okay, is the byte there a value of, okay, what is IP gonna be? 1 2 3 4 5 6 7 8 9 10 11 12. It should be 12. So it should be 12 here. Let's see if it works. It fails. CPU 1 is this one instead of this one. So stack pointer. Oh yeah, because this should be -1 because we pushed something to the stack. It works. Yes. So push and pop works. Oh no, push works. I don't know about pop. Okay, let's do pop. Memory address at say RA. No, let's just say at 700. Wait, no. We want this to be 1673. Let's do 1673. Yeah, hex 1673, hex 1673. Let's see if we can like assemble this again. Okay, so we pop. So what is the opcode for popping from the stack? 12, not 12, 1, 2. So that's 16. Sorry, plus 2. This is the opcode. And then, how many arguments it has? Does it have? So it has one argument. So it has argument 1. Argument 1 is existent. That is. And it's an external argument, and that it has a byte over here, not a byte. 64-bit number over here that it needs, and it's used as a memory address. Yes. Well, this one, yeah, it doesn't have argument 2, so we're not gonna set that to 1. What else? That's literally all the data it needs. So now we want to check for 1673, so we're gonna add 4, and then we're gonna say, hey, is this value 12? And if the value is 12, then it should be good. And then now we want to set stack pointer back to what it was originally when we set it, because we popped the stack after we push. Oh, it failed. Fail. Actual is 0 when I expected it to be 12. Oh, that means we're not setting it to... That's not good. What did I do wrong? Fail. Actual is 1.6. Expected is 12. But we know that this one is... Okay. Okay, let me go back to... Okay, let me go to the code where I interpret... Where it interprets the pop instruction. Pop. Oh my gosh. Push and pop have the same case. Oh my gosh. Okay. It should work now. Can you work, please? There you go. It passes. We'll do one more time. There you go. It works. It works. Third time's a charm. Yeah, it works. Good. Okay, so we know that push and pop works. Now what do? We want to check scall. So my CPU is gonna have like a special kind of feature where the code can basically ask if a piece of code can be regularly called at an interval. That is every like given seconds can it be called. And I think that's good because it shows that the architecture is not really like a real life architecture, but it's supposed to be for a game. So that's fine. All right. So scall and decall. Yeah. So scall basically makes a function get called every so and so seconds, and decall basically removes that kind of regular calling to that function. But yeah, so I want to do that, but first of all, I'm gonna need to like do a kind of like thing here. Start state. Yeah, so this start state and end state basically allow me to set basically the start state of the CPU and show and then compare the CPU's ending state with the state that we that my code expected. The state as in like registers or like maybe memory that's I don't know edited. But yeah, I kind of don't want to do that. Because like look, okay, if I look at my code here, it's called argument 1 makes argument 1 regular call every argument 2. That literally, okay, I'm sure this code works. So this not scall is not push either. Okay, good. And then decall argument 1 stops making argument 1 regular call. So argument 1, okay, so this instruction makes stops no, makes okay stops argument 1 from being regularly called. Um Yeah, I think this is fine. So it goes through each of the arrays, each of element in the array. If the address is what is given, this dot s calls equals. Okay, so this basically just removes the thing, the data entry. Yep, not gonna break, but I minus minus. Okay, good. Alright, whatever. Lewis slash. Alright, so now, okay, let me see. Port. Set port. Get argument one. Get argument two. Okay. Get port. Argument one. Set argument two to get port. Argument one. How to? Yeah, I think that makes sense. Default. This dot set flag. CPU flag position. Not faster than light. FT. Fatal. There you go. Um, it should return. Okay, good, good. Alright, I think this makes sense. Yeah. So this should. I think this works. I do not want to check it because like I don't want to. Maybe I should. Uh, I mean, oh my gosh. I mean, we have 1,000 lines of code, so like, ha 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 ha. Okay. I don't know if I want to check that. So this does a test. I'll just like console.log. Like, okay. Oh wait, no, we don't want to console.log memory. CPU dot execute get flag get memory. Let's set that to. And then I'll just temporarily luau console log. Okay. Uh object stringify CPU. Let's go, and then indent that too. Ending state of CPU. Okay, this starting and end should be two. CPU dot memory is null, undefined. And after we stringify that, we can set CPU memory back to temporary, and then get on with our lives. So, I'll just open that. What is that? Oh, those are the ports. Registers, ports, S calls. Okay, so now, now I can actually just like S call, like add some sort of like data here. Like, I don't know, man. Like, okay, S call. We want to regularly call a function at like 5, 6472 every like 10 seconds, let's say. So okay, let's see the opcodes. Okay, let's manually assemble again. So hex 6572 10.0. Okay, actually maybe not. Okay, 6572 hex 2. Okay, 2 decimal 25970. Yeah, 25970. Let's just set it to that. Okay, now, all right, what is the opcode for scall? I wonder. It's 13. Okay. Hex 13. So that's here. Okay, so now we do yeah, it has yeah, its first argument, yeah, is existent. Its first argument exists. Um, it's an external argument and it's not a memory address. And same for this. Okay, so now, yes, so that's definitely what we want. And we're just gonna copy this, RA, the IP, let's do that. So argument 1 is gonna be internal, and, well, it's gonna be 0 then. Yeah. I'm so smart. Actually, I feel like it should be like this. Okay, so it shouldn't be 0. It should be like, it should be this number. 2 decimal. Let me open a JavaScript terminal. Okay, let's run this. 4, 4, 5. Okay, well, what did it say? Okay, 454 2 0 0 1 6. Yeah, that's correct. And then we'll do decall. Decall 25970. So, decall is going to be the instruction right after. Okay, now, no, this is not going to be in there. Let's see. Yeah, oh yeah, that's true, because I did do this. Okay, so yeah, so that does remove it. Okay, good, good. Let's set it to like 0.2. Pass. Okay, oh, and this one, yeah, yeah, yeah. That definitely is working. The port thing, I don't want to do that. Like, I don't want to test that. But you know what? Like, might as well, right? Like, no, okay. What is something else I can do? Something else I could do is to create a Lua, not a Lua, a JavaScript, not JavaScript, a TypeScript function that kind of like, I'm saying like, uh, make sure that it's finite. So it's like the equivalent of math.is is finite. Yeah, yeah, math.is is, wait, no, finite? Wait, what do you even do? Number dot finite is finite. There you go. Unlike the global is finite, number dot is finite doesn't forcibly convert. Is finite. Yeah. So we're just gonna create our own function here. So like, function luau is finite. Val v should be a number. I'm gonna return, hey, v is not equal to nan, and v is not equal to infinity, and v is not equal to negative infinity. This condition will always return true. Wait, what? Why? Did you mean number is nan? Yeah, that's what I meant, but that function just doesn't exist in Lua. Okay, that does exist. just strangely enough, Roblox nil. What? Nil value, so it doesn't exist. Okay. Ah, yeah. Number dot is net. Okay, but okay, print. Why you want it to be? Oh, that's a good point. Um. Oh, yeah, yeah, yeah. It's because I wanted to. Ah, okay. Custom language. That's a very good question. Well, because I plan to make a game where it involves like the player doing some coding. Um, and you know, I could just like make it Lua or something, but I don't think that's. I mean, that would be the easy route, but I don't like that. I don't like Lua. I don't like. Yeah, I don't like the Lua language. So I'm thinking like, why not just make it my own, custom programming language that's more C style, if you know what I'm saying, right? Because I prefer C style languages rather than Lua. Um, but yeah, that's why I wanted to make a custom language. Um, Also because it's something that I've tried to do a few times before, um, but none of them were like that successful. Actually, only one of them, but like I abandoned it because like school. But yeah, I wanted to challenge myself, and because uh, I want to make a game that involves coding, kind of. Um, but yeah, that's why I made a custom language. It's yeah. So the language's style is like okay, where the heck is that? Yeah, it's similar to C. Yeah, it's similar to C as you can see, right? Like, I mean, all this code is commented, but like, yeah, it's similar to C. Um, and so yeah. Okay, does that answer your question or no? All right. Wait, what was I gonna do? Oh yeah, I wanted to make a custom like is finite function. Okay, this is not working. Uh, okay, if I try to write a little function, okay, function. No, is that how you define a function? I kind of forgot. How do you? Okay, I need syntax highlighting, but okay. Um, function is finite. I'm gonna get a v. Uh, end. Is that correct? Expected. Uh, expected that one near. The heck does that mean? Like what? Oh, so it did not expect a type annotation. Okay, okay. Yeah, is the game going to be like an engine, like Roblox? No, 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 no. The game is just gonna be like a game within Roblox. Like you know how Roblox has a bunch of games, right? The game is gonna be like one of like an experience. I think that's the name. Yeah, the game is gonna be like an experience on Roblox, not like a game engine or anything. Um, but yeah, I don't think I'd be able to create a a game engine that's like as fully featured as like Roblox Studio. So like that's not gonna happen. Uh, okay, so if I do return v is not equal to nan, and sorry, that is not how it looks like. That is not how Lua code works. I really hate how Lua uses that tilde operator in order to say not equals. Like that is just so like unintuitive to me. Okay. And v is not equal to infinity, and v is not equal to negative infinity. So if I just do like print is finite 1, nan, infinity. Oh wait, no, that's not a thing. It should be math.inf. Math.nan. Okay, yeah, I forgot. Attempt to perform arithmetic on a nil value. Field inf. What? How to get infinity value Lua. That is C++. That is not what is important. Oh, it's just math.huge. Okay. But I'm pretty sure on Roblox, Luau, which is a dialect of Lua, it's math.inf, but true, true, false, false. Oh, it should be math.huge. How do you get the type? Oh my gosh. Print type of 1. Yeah, okay. Is that equal to number? Okay. Should be string? Yeah, okay. Return v, type of v is number. And yeah, something like that. I think that's good enough, yeah. So that is our Lua function. How am I going to translate that to JavaScript? Not JavaScript, TypeScript. That is the question. Okay, let me see. Does it support nan? Let A is nan? No, it's just math dot. So math dot nan? What the? Oh wait, no, I don't think that's needed. All I need to do is to say, hey, is it an integer? How do you do that? Lua, how to know if number is integer? Math.type allows, oh, okay. That's a regular Lua. What about Luau? Oh well, I didn't read the entire post, but this is the updated method. What? Okay, I open this, yeah. It float, oh my gosh. Oh, bro. That is so simple. You just like mod by what? Okay. Okay. Actually, honestly, I feel like I should just do math.floor for any one of these. Yeah, I should just do I should do this else we're gonna do math.floor. So anytime I use this is ROM. Array, okay, math.floor. Okay, oh wait, no, stop. Before I accidentally do more, I need to create an interface function that kind of like makes it easier for me to translate from Lua, from TypeScript to Lua. So okay, Luau, is, no, math, well, what math? I need to floor it. There you go. So v number, return math.floor, but wait, I already did that? Okay, that's funny. Okay. Okay, that's funny. I already made that. Okay, whatever. Okay. We'll do a math.floor. No. Luau math floor. Luau math floor. Luau math floor. Because if I set, say, let me open a terminal. That is the wrong, not a terminal. Whatever this was called, the console. Um, if I do 1 is less than 9, yeah, that's false. 1 is, I mean, if 1 is less than infinity, but then is infinity less than a sort of value? Then the answer is no. So yeah, it's fine. So we don't need to check whether it's non-infinity or negative infinity. We just need to make sure that it's an integer. So I guess we'll just floor that. Um, okay, wait. Let me see. Yeah, this should floor it. Luau math floor. So that if a decimal is like submitted, it's not like no, it's not gonna break anything. So luau math floor. Um, yeah, there should be luau math floor. This one, oh, that's the constructor. That's okay. Not this one. Luau math floor. Okay, luau math floor. Floor. Okay, good. So now we're just gonna say, additional notes. Additional notes to the CPU, I guess. Oh, no, just additional notes in general. If a port number, memory address, register code, etc. is given as a bit representation, is given as is a decimal, right? Is given as a decimal. It should be, there should be a space here. Decimal value. That fractional component. The fractional component will be truncated, and I think that's good. Yeah, truncated, i.e., floored. That should be good. Okay. Or other data that are supposed to be integer values, integers, right? Datum. I guess we'll do datum. That is, whoops, supposed to be an integer, right? It's given as a, no, is a decimal value. Okay, is a decimal value. The fractional component will be truncated, i.e., the given datum is floored. Floored. Okay, that should be good. However, the issue, is there any other issue? I mean, wait, let me check my to-do. Make CPU actually do something with scalls. Oh yeah, that's what I'm supposed to do. Make CPU test and CPU and test reflect the new changes. Yeah, I did that. Yeah, the simplify instruction set, I can get rid of that because that's what I did last night or something like that. Yeah, I think that's what I did last night. Make CPU actually do something with scalls. Uh, okay, I guess we can do that. But that means that this function should get time. But do we have os.time? Yeah, we do have os.time. Good, good. But okay, that means I need to create another function that interfaces between TypeScript and Lua. So luau os time return. Do we have in TypeScript? Do we have os time? Okay. Okay. JavaScript how to get time. Wait. So what does, okay, OS time luau. Okay, what is OS time supposed to be? Uh, oh yeah, I think we want to do, okay, tick is number of seconds. We don't want that. Time is, number of time in seconds since the game instance has started running. Okay, and then os.clock turns the amount of CPU time used by the. This value has high precision, about 1 millisecond. Okay, I think we want OS clock. Yeah, OS clock is definitely what we want. Not OS time. Um. Okay. How to get OS clock in seconds? JavaScript. Oh, well, we could just do like date dot. Okay, what is date dot now? Current time in milliseconds. Oh, date dot time. Okay, run. Starting timer. Seconds elapsed. Okay, so all you gotta do is, okay. Okay, so literally just date dot now, and then just divide by like 1,000. Okay, good. Uh, so date dot now divide by 1,000. And okay, so the Lua code is supposed to be os dot clock, os clock luau. Hmm, Roblox. Oh, wait, that's return elapsed time in seconds since an arbitrary baseline with sub-microsecond precision. Good. Alright, return os.clock. Yes, basically. Milliseconds divided by 1,000. Yeah, that should be fine. Okay, good. So now, if I do console.log, I guess, the luau os clock, not while, set timeout, I guess. How do you even do this? Handler, um, console.log, luau os clock, and then it should be 2,500 milliseconds from now. Okay, that's very useful. Okay, let T1 be equal to this. This one minus T1. This should give about 2.5 seconds. Okay, good. That seems to be great. Yeah, okay. So that's good. That's working. So that means I can like copy and paste this function now into my code. To my library. Okay, there you go. Make sure to save that. Okay, this one at the top. Let me just put this here. Yeah, I'm putting my code basically into like one file per project because like I can only like convert one file into Lua, one TypeScript file into Lua at a time for this using Roblox TS, which is what I use. Um, but anyways, but obviously that is not good uh practice. Okay, now that we have Lua OS clock, now we can actually like do this. So, all right. Okay, I think this thing needs another argument, which is not argument, another datum, which is, okay, delta and like the time since it started. Or time since last, no. Time last call. And so this should make a bunch of errors. Time last call. There it is. Time last call will set it to negative, well, that is like negative big value. Oh, wait, time last call. Time last call. Yeah. So that means this should be time last call, be number. Okay, good. Now I actually want to do this. So this is do cycle. Let execution result. Let exec result. We'll just return exec res, and we'll make sure this is a boolean. Now run any what's it called? Run any scalls if needed. Okay, run any scalls when, well, okay, if the time is right. Okay, so for let I equal 0, I is less than this dot scalls, okay, low array length. Okay, if, okay, so if this dot scalls I is equal to, sorry, dot time last call minus, okay, let me get the time right now. Get OS time. Let's, okay, let me do const. T1 is equal to, OS time, OS clock, I guess. If this is, okay, minus T1, right, is, if the, I guess the difference, is greater than this dot scalls I dot delta, then we're gonna actually call the function. Actually call the function. So whatever. Okay, T1 is equal to like, I don't know, this dot scalls I dot time last call is gonna be T1. Okay, reset the timer. Okay. And to call the function, all we gotta do is this dot set register. So we're gonna set the the instruction pointer to the function location. So this dot scalls I dot address. So the function address, function code address, I guess, and then that's basically it. And yeah, that's gonna be our thing. Now, actually, in the future, I might actually just, instead of like doing 0.1 or 1, or like, instead of having the delta as seconds, it could just be like number of cycles. Yeah, I think think that would be useful. Um, I feel like I want to change that now though, so that I don't have to have headaches later. Okay, so okay, delta. Okay, I guess I'll just. I mean, I don't know. Lua, should I should I base this on the number of cycles the CPU does, or should I base this on the time of the actual computer of the user, like the actual player? Uh, hmm. Is there any disadvantage to using cycles per second? Because if you know how long it takes, if I put in the game and tell the player in the game, hey, this is how many cycles per second that the CPU does, I don't think it's an issue. It shouldn't be. Um, yeah, it really shouldn't be. And if the player wants to actually get the OS time through the virtual machine, then they can like do some port thing. I don't know. Um, they can like communicate with like the ports, one of the ports of the computer, and maybe I'll program or whatever. But so I think instead of this, I guess I'll do like 100 cycles, and this is 50 cycles. Okay, yeah, this I will have to update the documentation. So, okay, I'll just put like to do. Okay, I'll do make CPU use cycles um instead of seconds for scall, and then make update documentation to reflect change. Okay, reflect the change. Okay, so we'll go to delta. What do we do here? And okay, I'll add to the CPU the number of cycles that it has gone through. So n cycles. I guess we'll do cycles. We'll set that to 0. And then like after every do cycle, I'm gonna like increment cycles. Plus cycle. This are cycles. And then so like time since last, is it called? Okay, and now um okay, so the code that's relevant here. So I guess I'll do like delta okay, delta cycles. I'll just like try to find the errors. Okay, good. So now, okay, let me actually edit the scall. Okay. Oh, whoa, let's save our changes. Okay, this one right here. So instead T1 is not going to be that. Plus cycles. We'll do that at the top. Actually, I guess I should set the cycles to like 0. Oh, no, the default value. So that's in hex. Yeah, this should be like 0. Oh yeah, no, not this one. This one. Because then this would like make the function run immediately once it calls sets cycles or something. I don't know. I'll just set it to just cycles. Okay. So if this dot s calls, right, minus this dot cycles is greater than, yeah, delta cycle. Okay, then we'll do this, and then we're gonna reset the timer. Yeah, and so through this, that means that the user can know, okay, since this function is called every, say, 20 cycles, I need to make sure that the function that I'm writing, that I want to have it be called every so-and-so cycles, that function is well below, takes well below 20 cycles to execute, right? So that it's not like got an infinite loop or whatever, right? It's not good for it's not good for the game. But yeah. Um, All right then. So reset the timer. All right, whatever. Right, what else should I do? Okay, let me update the code here so that it's every, say, 50 instructions that it does. So okay, so because I don't want it to like 50, 100. I'll delete this. Yeah, so it has a bunch of calls. Cycles last call. Delta cycle is 10. Yeah, no, this should be 100,000, I guess. Alright, good. So now, actually, before I want to like first flatten it. So I want to flatten this, as in not flatten. I want to. Oh wait, never mind. That's not, no, delta cycles needs to be flattened. As in floor. So math.floor. I'm gonna do okay, now I just need, so tomorrow I'm gonna need to update the documentation. So now, if I paste this code to Lua, or not to Lua, to type, yeah, to this code which converts it into Lua. Oh, something is wrong. Okay, that's not good, that's not good. CPU.memory. Undefined is not assignable to, oh. Well, I could do just memory.array. Okay. Okay, let me copy and paste this back to the code here. Oh wait, no, this is not a... I want to copy it. Like, I don't want it to be a shallow copy. Um... Wait, can I just do this? Delete? As hopefully that's legal. What? The operand of a delete operator must be optional. What does that mean? Okay, I guess not. So that means we're not gonna be able to do it. Yeah, maybe we don't need to do that. We can just comment that out, I guess. Okay, whatever. And okay, let's move on to this error. Math dot oh, should be Luau math floor. Variable data is used before being assigned. Oh. Okay, that's fine. And this one is okay, the various library functions. So that's fine. Let me just copy this, copy this, copy this, copy this, copy that. Okay, now I'll just like what? Oh, I didn't change it. Okay. Um, yeah, I'll just set this to like hex 211 because like why not? We're just gonna fail silently. That should be good. And then now I just copy and then paste again. No more errors. Okay, good. Now I just need to like go through each of these and oh wait, never mind. Oh yeah. Comment this, comment all of this. What is this? Operator. Oh, there you go. Alright, so I've got the code here. 1,000 code. Time to open Roblox Studio and actually like, okay, let me like, first of all, where is it? Where is the pillar screen? Okay, okay, let me like turn, let me just hide things first, in case I, leak some of my, information. Okay, now I'm opening up Roblox Studio. Okay, my CP, not my CP, my laptop is turning into a jet engine. Okay, there you go. Roblox Studio is loaded. Now I just open the game I'm gonna test it in. Okay, let me see. Okay. Okay, I have Roblox Studio here. Let me share my screen, full screen. There you go. Okay, I have Roblox Studio. No, that's the wrong one. Now I just like copy this, open Roblox Studio. I guess I just like paste the code here, and then like, is this correct? Set arg, yeah, set arg, yeah, something like that. And now let's like set this. No! Attempt to perform. No! What? Okay. Okay, I just leaked my username, but whatever. Um, but if I run it here, it works. Attempt to perform arithmetic add. So it's in function set flag. Set flag. Oh, okay. Arithmetic add on nil and number. So line 808. Oh, there's one of these things. Okay. So it's probably this one right here. Red codes RF. Uh. Oh! Red codes. Okay. RF. It's not. It should be FS. Not RF. Now I think if I copy this code, if I copy only the code that I need to copy, paste it back here. Nope, that's the wrong keybinds. It doesn't do what I want. Okay, this is the, there it is here. So I just like paste that in and like, okay, now I control F set flags. It still has FS though. Oh wait, no, FS is correct. Yes. Okay, good. Now I just copy that. And I paste it over here. How do I clear the? Okay, there you go. I cleared the console. Oh, what is Roblox? Oh, okay. Sorry. I wasn't paying attention to the chat because the chat was blocked when I was okay. I remember doing the %1 for my CS class. First, oh, nice. %1. Okay, so is that for measuring whether it's a integer or not? Also, what is, oh, Roblox TS is, it basically converts TypeScript code into Lua, which is what Roblox uses, right? Or Luau, which is the Lua dialect for Roblox, right? Um, yeah, and yeah, that's what Roblox TS does. It's Roblox TypeScript. It converts TypeScript into Lua. Um, yeah, you have to check if it's an yeah. Okay. Let me like copy, like, delete this and then paste that. Failed. Why? Okay, never mind. This should, wait, what? CPU 2 instead of 0. Okay, so if I set this, if I run this again, this should fail? Okay, it failed. Okay, and it failed for the exact same reason. Yeah, CPU 2, so that means the third register is 2 rather than 0. 0, 1, 2, yeah, the third register. That would be, okay, whatever. 2 and 6. Oh, that would be the flags register, because that's what I said in my ISA. Instruction set architecture. There you go. Great. Good. That should be okay. So I'll just like update that. It should pass. Yeah. Okay, that makes sense. Yeah, because they're equal. Okay, that's good. That's interesting. Wait, no. It's because there's less. Okay, 0 is less than 1, so that makes the flags register have a value of 2. Okay, good. So all right, this works. Okay. All right, so let me like clear that. Okay, I'm gonna close Roblox Studio. Did what I needed to do. So that means the library basically works now. All I need to do is to just update the documentation for my ISA in order to make sure that it reflects the change that I made earlier. And yeah, after this, I'm basically ready to make an assembler that would convert human readable code into human readable assembler code into the bytecode, and then once I'm done with the assembler, I can actually write the code generator for my custom like compiler here. And yeah, I mean, all right, I guess that's gonna be the end of the stream. Thank you for watching. I know I probably just said a whole lot of nonsense, but yeah, thanks for tuning in. Have a good night. Probably it's probably nighttime where you are. I don't know. But yeah, goodbye. Have a good day or night or whatever, and yeah, bye.